Okay, this is going to be the video for the first part of Chapter 16 for AP Statistics on random variables and combining and transforming distributions. To start with, I'm just going to talk about a scenario here, and that'll lead to some definitions. So let's take a look at this. What if we had a small raffle at a high school football game where there was just 100 tickets that were sold? One ticket was designated the winning ticket, so that one paid $50 if selected, and then there are 3 runner-up tickets that will pay $5 each. And then the other 96 tickets pay nothing. So those are losing tickets. So if you were to play this raffle every week for many years, what would you expect your winnings to be on average per week, right? Well, sometimes you'll win $50, right? But that's only going to happen 1/100th of the time, right? Sometimes you'll win $5, but that's going to happen 3/100ths of the time because of the number of tickets. And then you could win $0, which will happen 96 out of 100%. 100 times, right? So if I think of these 50, 5, and 10 as data values, I'm going to use an X for that. There's one possible value, that thing that can happen, and then multiply that by its probability. And I have some other value outcome multiplied its probability, and some other value for the outcome times its probability, and you add those things up, you're computing something called the expected value. Okay, and in this case, that would add up to, or compute to 65 cents. That means that in the long run, you would win 65 cents per week. You would never actually win 65 cents, but it would average out to 65 cents per week, okay? And so this is like a mean, except that it's an average, but it's been weighted by the probabilities of the different outcomes. To see that, let's see what would happen if instead there were an equal number of tickets, like 33 out of 99 tickets of each type. So there was 1/3 of the tickets won $50, and 1/3 of the tickets won $5, and 1/3 of the tickets won $0. If you computed that data, those values, you would get a higher expected value because now there's more likelihood of winning, right? But I want to show you something. If you compute this expected value here, I'll call EV, 50 times 1/3 plus 5 times 1/3 plus 0 times 1/3, that forms the fraction 50/3 plus 5/3 plus 0/3. And so that's the same, since there's a common denominator of 50 plus 5 plus 0/3. And that's really just finding the average, right? If we add things up and divide by the number of total, we're finding the average, right? So if I had equally likely cases, I could just say, well, you could win 50 or 5 or 0, and I'd add those up and divide by 3, and that would give me the average winnings per week, right? But what the expected value calculation allows us to do is to allow these probabilities to be different for each outcome. So it's a probability weighted average, okay? All right, and then the other thing I want to point out here is that these values are almost like values in a data set, right? $0, $5, $50, they form possible values. So if you think of them as kind of like values in a data set, then the frequency, the probability, is how likely each of these are to happen. If you graph that like that, it forms a distribution, right? This is a skewed right distribution, and that expected value is like the mean of that distribution, okay? And then here's a uniform distribution if all the values are equally likely, right? So I want you to think of the possible outcomes of a random process, like say playing a lottery, as values that form a distribution, all right? Okay, so to talk about the values that occur with a random process, we can define something called a random variable. Typically we use capital letters like X. So a random variable, it's a variable that represents the possible values of some outcome of a random process, like something different than happens every time you play the lottery, okay? In algebra, when we have a variable, it's a placeholder for a specific value, and usually we're trying to solve to find that value. But in statistics, a random variable is a placeholder for a value which is expected normally to vary. We expect it to vary around. And if I take the possible values of a random variable times the probability of each of those outcomes, and then sum them up, that's what this means, we're finding what's called the expected value of the random variable X. And usually we use the symbol mu because that's a symbol for a mean, okay? All right, so whenever we assign probabilities to each value of a random variable and we figure out the probabilities for each one, that's called building the probability model. All right, so with that much, we should be able to switch and do the first problem in the required practice packet. So if you happen to have that handy, I'll actually get that out and we're going to try this. Pause this, read it over, see if you can see what's going on, and then unpause, and I'll show you how to do this. Okay, so this says imagine an experiment in which you flip an unfair coin. So the probability of getting heads here is 3/4 of the time you get heads. And that means the probability of getting tails is only 1/4 of the time. So it's a weird coin that's weighted so it lands on heads more often. First, it says write out the sample space for the experiment outcomes. Okay, so I'll write a sample space out. We're flipping a coin 3 times. And that means what could happen is you could get all tails. You could get 1 heads, and the head could be first, or it could be second, or it could be third, right? Or you could get 1 tail, and the tail could be first, or the tail could be second, or the tail could be third, or you could get all heads. Those are the possible things that can happen in the scenario. Okay, so that's the possible scenario here. Sorry, I keep checking my screen here because I recorded a video where it didn't record the screen, and I'm making sure it's staying alive here. All right, then it says, let's let a random variable x be the number of heads specifically in the experiment. Below each entry, let's list the value of the random variable. So since this represents the number of heads, there were 0 heads here when we had all tails, right? We had 1 head here, 1 head here, 1 head here, 2 heads there, 2 heads there, 2 heads there, and 3 heads here, right? Okay, I don't know, my microphone might be clattering. Hopefully that's not too disruptive. All right, so then it says now list the possible values of the random variable. So if this random variable represents the number of heads, the only possibilities are you could have 0 heads, or 1 head, or 2 heads, or 3 heads, right? So what we're going to do is try to figure out the probability of each of those values of the random variable happening, right? So what we could do is say, okay, how many ways are there to have 0 heads? Well, there's only 1 way. Tails, tails, tails. So what's the probability of that? Well, the probability of the first row being a tail is 1/4 because it's an unfair coin, right? And the second one is 1/4, and the third one is 1/4. And because we'd have to have a tail and a tail and a tail, and is multiply, we would multiply. So that turns out to be 1 out of 64. Okay. Okay, the 1 head case happens 3 different ways. You could have heads, tails, tails, or you could have tails, heads, tails, or you could have tails, tails, heads, right? All right, so the probability of heads is 3/4. Tails is 1/4. Tails is 1/4, and you'd multiply that. And then because it's or is add, we can add the probability of this second case, right? 1/4 chance of tails, 3/4 chance of heads, 1/4 chance of tails. Or, so plus, tails probability 1/4, tails probability 1/4, heads probability 3/4. Okay? And then that means we would have 3/64 plus 3/64 plus 3/64, 369. This would be 9/64 chance of having this outcome. And we could do the same thing for 2. For 2 heads, the ways are tails, heads, heads, or heads, tails, heads, or heads, heads, tails. Okay, and the probabilities there are 1/4 chance of tails, 3/4 chance of heads, 3/4 chance of heads, plus 3/4 chance of heads, 1/4 chance of tails, 3/4 chance of heads, plus 3/4 chance of heads, 3/4 chance of heads, 1/4 chance of tails. So that's going to be 3 times 3 is 9/64 plus 9/64 plus 9/64. 64, which turns out to be 9, 18, 27/64. And then the only way we get 3 heads is if we have heads, heads, and heads. The probability of that happening would be 3/4 for the first one, 3/4 for the second one, and then 3/4 for the third one. 3 times 3 times 3 is 27/64. Okay. Make sure my video is still live here. Yep. Okay. All right. So now we can create what's called the probability model, right? The random variable for the number of heads has the possible values 0, 1, 2, and 3. And below that, we'll write the probabilities. The probability is 1/64th of having 0 heads, 9/64ths of having 1 head, 27/64ths of having 2 heads, and 27/64ths of having 3 heads. And if you add these probabilities up, they add up to 100%, 64 out of 64, because a valid probability model always has all the outcomes probabilities summing to 100%. Okay, but if you were to graph this distribution, right, I've got different outcomes here, right? 0, 1, 2, 3, the number of heads, right? There's a pretty likely chance, 27 out of 64, of having 3 heads, the same chance of having 2 heads, much less chance of having 1 head, and a very small chance of having 0 heads. Okay? And what I'm saying is that the expected value, if we were to compute the expected value for that, which would be the mean, we would take each of its values, like 0 happens 1/64th of the time. We could add on 1, which happens 9/64ths of the time, 2, which happens 27/64ths of the time, and 3, which happens 27/64ths of the time. And if we compute that, we end up getting 2.25 heads. So the average of this distribution is 2.25 heads. That's where the mean of this distribution of the possible values of this random variable are. So the values of the random variable, they almost look like a distribution of a data set, right, where these are the possible values. Okay. And it shouldn't surprise you that since there's a distribution, we could also define a standard deviation, right? So the way that's defined is, now let's see, are we doing that next? Where do we talk about that? Oh, yeah, let's take a look at the notes. Let me go back to the notes for a second. All right, so when we lift this probability distribution out, where we have the number of heads and then the probabilities, that forms a distribution, right? Like, let me repeat it over here. We have 0, 1, 2, and 3. And then we have 27 out of 64 chance of 3 and 2, but only a 9 out of 64 chance of 0 and 1. And when we calculate the expected value, which we did by taking the sum of every value times its probability, we got 2.25 heads, which is the mean of this distribution. You can also have something, although we don't see it as frequently, a cumulative probability distribution. So if you want to show that there's like 1/64th chance, and by the time you get to the ones, you've included a total of 10/64ths, and then you add on the 27/64ths to get this, and then by the time we get the last outcome, you've seen 100%, like an ogive. That's called a cumulative probability distribution function. But most of the time, we're just dealing with the probability distribution itself, the model. All right, so it shouldn't surprise you that there could be also a standard deviation here, all right? And the way we'd have to calculate it if we did by hand is using similar methods to what we did when we did it by hand for data. You would take the data value minus the expected value, the mean, and square that to make all the differences positive, and then multiply by the probabilities, and then sum those up. Right, so to do that for this case, you'd have to say, all right, now that I know that the mean, the expected value is 2.25, then if my data values are, let me take the probability function again here so I can, not that, I want to take this, copy it, so we can see it. So if I wanted to compute the standard deviation, we could do this. We could say, all right, well, first we're going to start by computing the variance, which is we're going to take every data value, right, and find its distance from the expected value, the mean, square it, and multiply that by the probability of that. And then this one, 1 minus 2.25 squared, times its probability, 9/64ths. And then 2, right, that data value, how far away is it from the average, times its probability. And then finally 3 minus 2.25 squared times its probability. That is a lot of work. And then we're not done because the variance is the standard deviation squared. So then we would have to take the square root of that to find the standard deviation. Okay, so instead of doing it that way, what we typically do is use a calculator. So let me move this over, and we will get a calculator on the screen here. Okay, so what we could do is, let's clear our lists, and then go into Stat, Edit, and then for list 1, what we're going to do is we're going to enter the data, the possible values of the random variable as if it was a data set in list 1, and we'll put the probabilities as frequencies in list 2. Okay, so I'm going to enter 0, 1, 2, and 3 in list 1, and then for list 2, I'm going to put 1/64th. For 1, it'll be the probability 9/64. For 2, it'll be 27/64. And for 3, also 27/64. And then we can treat it as if this random variable is a data set and go Stat, Calculations, One Variable Stats, and run statistics on list 1 using the probabilities in list 2 as the frequencies. And sure enough, there's my expected value there as the mean. The mean is 2.25. If I calculated this out by hand, I would get the standard deviation, and that shows up here on the screen as 0.75. This is the number of heads here. So we would get on average with this unfair coin 2.25 heads with a standard deviation of 2.7 heads, but it's not symmetrical. It's skewed left. Okay. And notice how the calculator didn't even bother with a standard deviation as a sample, because it knows when you enter probabilities in list 2 and they add up to 100%, it knows that you're seeing all of the possible outcomes, which really constitute a population. So they don't give the sample standard deviation, only the population standard deviation there. Okay. All right. And these random variables we're talking about here are for discrete random variables, which means something where we're counting something, like the numbers of heads or the numbers of girls or the numbers of boys or something like that. It is possible to have a continuous random variable instead of a discrete random variable. That would be something like, say, the heights of people, right? Or weights of people, because there's an infinite number of values. And so we have to resort to other structures for the distribution, for example, the normal curve, right? That can find area under that curve, right? But this is a structure that's specific here for discrete random variables. Okay, to finish off this, we're going to do the second problem in the required practice packet to finish this video off. So let's go over to that. All right, and I'll just ask you to pause the video and give this problem a try, and then unpause and we'll work it. Okay, so here it says let X be a random variable that represents the number of boys in a 3-child family. Find the expected value of the number of boys, the variance of X, and the standard deviation of X. Okay, so we're assuming binary gender here is about number of children of each gender in a family, and there's 3 children. So maybe we would start by listing the sample space of the outcomes, right? So if we have 3 kids, right, they could be all girls, right? We could have 1 boy and they could be first or second or third in order. We could have 1 girl and 2 boys, and the girl could be first, or the girl could be second, so B, G, B, or the girl could be last, third, or we could have all boys. So 8 possible outcomes. If we want to find the expected value, we have to figure out what the value of this expected value for number of boys is. So for the girl case, it would be 0 boys, right? 1 boy for that outcome, 1 boy, 1 boy. 2 boys, 2 boys, 2 boys, 3 boys. So hopefully you'll see what a random variable does is it maps numerical numbers to different outcomes. It's like a map that connects numbers to outcomes. Okay, and then if we want a probability model, what we could do is now just list the individual possible outcomes here and come up with the probabilities of each. So in the probability world up here, I take one particular outcome, like say this one. There's a 50% chance of having a girl, 1/2, a 1/2 chance of having a boy, 1/2 chance of having a boy. Half times half times half is 1/8. And so these are all equally likely and the same. Every one of these probabilities is 1/8, right? This is an equally likely scenario. 1/8 for this too. Okay, so then the 0 case only happens here. So there's a 1/8 chance of that happening. 1 boy happens here or here or here, so we would add these because or is add, and we would get 3/8. 2 is this or this or this, so we add that up and get 3/8. And 3 boys only happens in the 1 scenario. So here's my probability model. And then what I would do is enter this in list 1 and this in list 2 and let the calculator tell me what the expected value in standard deviation is. So if I were to go back and clear my lists again, and then enter 0, 1, and 2 for list 1 and 3. And then for the probabilities, we'll put in 1/8 for each of those. Nope, 1/8 for the 0 case, sorry, 3/8 for the 1 case, 1 boy. There's a 3/8 probability of having 2 boys, and there's a 1/8 probability of having 3 boys. And then we could run one variable statistics, stat calculations, one variable stats on list 1, list 2 again, and find that the expected value of x is, what is it? It's 1.5, this top line here. 1.5, and the units here are the number of boys. Okay, what I'm going to do is do number C next, because the calculator gives me standard deviation as 0.866 boys. And then I would know, okay, the variance is just the square root of the standard deviation, because standard deviation squared is variance. I'm sorry, the other way around. Yep, variance is standard deviation squared, because standard deviation is the square root of variance. So variance is standard deviation squared. So I could just take the 0.866 number and square it. And 0.866 squared turns out to be about 0.75 units or boys for all this. All right, so that's how we would do that problem with expected value and standard deviation. And we'll pick up the rest of this unit in a second video.